Hi everyone, my name is Sheng-Kai. I'm from the Department of Power Mechanical Engineering, National Tsinghua University, Taiwan. Today, my topic is CMOS chip for solid-state tactile force sensor. This is the outline for today's presentation. Firstly, I'm going to introduce the background of the tactile force sensor, and then I'm going to point out my motivation and design concept. And then I'm going to introduce the fabrication process and results. Immediately following is the measurement and discussion. Finally, the summary. Let's get into the introduction first. Tactile force sensor is a medium to capture the information of touch and force. It has already been employed into several application fields such as robotics, engineering, medical tools, and consumer products. In conclusion, the tactile force sensor information is very useful and can be extended to act as a human-machine interface. This is the current commercial force sensor. It can be divided into different category by the different application platform. One is the strain gauge based low cell force sensor and the mass based force sensor. For the low cell, it has a high reliability and accuracy, but it is very expensive due to the precise and discrete assembly process, and it is very bulky. And it has a force resolution limited into 10 millinewton. However, for the mass force sensor, it is relatively cheap due to the batch process of the MEMS platform to implement the sensing chip. And it is relatively compact into the millimeter scale. And the force resolution can be even downscaled into millinewton. So today we're going to talk more about the MEMS base or the micro force sensor to be integrated into the target system. So these are some of the MEMS force sensor products by different companies. In terms of the sensing mechanisms, it can be divided into the piezoresistive and the capacitive. So if we take a look at the sensing structure, we can find a common features if that all of them requires the integration of the force content interface and the polymer interface, which will enable the effective force transmission to the sensor body because their structure is too small. So in this case, we know the design concern of the MEMS force sensor or micro force sensor. However, they will be suffer from different problems such as the suspended sinking structures. After you apply the large force on the sensor body, it may crack at the edge part of your device structure, so it will induce a smaller loading range. And for the process issue, it will have some process complexity to have some yield problem to realize this kind of a suspension structure. And the residual stress may have some effect as well, such as the induced structure failure if you have a very large warpage after the releasing, and also have some initial offset after you release your structure. And in addition, if you have a multi-layer staking, you may suffer from the CTE mismatch problem, which means if you have some thermal loading, you may have some thermal drift after you apply the environmental thermal noise inside. So let's get into the motivation and design concept. So the above mentioned issue lead to the motivation. Today, in here, we are going to present our solid-state micro tactile force sensor design based on inductive sensing to avoid the usage of the suspension structure. So in the process, we're going to use the CMOS platform to implement the coil and integrate it with the circuit to provide the advantage provided by the CMOS process. And we're going to use the polymer because it is a very simple process to fabricate. And at the same time, it is also a deformable mechanical spring and a integration medium to combine the CMOS chip and the force content interface. So we are going to use the stainless steel as a force content interface. At the same time, it can enable the signal variation to our CMOS coil. So this is a schematic view of our design structure. You can see several components on the CMOS chip, including the alignment marks to align the magnetic bump with the CMOS coil, and the other electrical components. And you can see the magnetic bump is right above the polymer, and the polymer is fully encapsulate our CMOS chip. If we take a look at the terminal, it will have some power or our signal output. And the cross-section view will provide more details. As you can see, this is the mentioned before, the polymer and alignment mark, and the electrical component, including the planar coil, and the MRM capacitor for forming the LC tank of the circuitry. And this is the ASIC to provide some of the processing signal. So after you apply a normal load into the structure, the gap between the structure, the magnetic bump, and the coil will be deformed. So the inductance of the coil will be detected. And by using the circuit LC tank, we can read in the frequency drift to detect the inductance output. So in conclusion, if we have our apply normal loading inside our system, we can detect it by using the frequency drift. So this is the circuit topology of our device, provided into 3 stages. The LC tank forming to form the inductance conversion into the voltage, and the level shifter to provide the common mode voltage into half of the power supply. And this is the output driver to provide sufficient driving current for our testing facility. This is our oscillation simulation results. In our case, our inductance is 181 nanohenry, and the capacitor is 50 picofarad to form the resonance at 52 megahertz. And note that this resonance is 10 times smaller as compared with our self-resonant frequency of our coil to prevent the noise. And we put it into the time domain simulation tools to see the periodic waveform signal output and demonstrate this phenomenon. And to further verify the inductance, inductive tactile force sensor application, we input a linear inductance signal output into our model to see the output of the frequency versus the inductance. And let's get into the fabrication process and results. Firstly, we will receive the chip prepared by TSMC 2P4M CMOS standard process. Then we will do the wire bonding and epoxy to protect our bonding wire. And then we will do the polymer molding and encapsulate our CMOS chip. Finally, the adhesion and assembly of our stainless steel sheet to form our device on the test. So this is the chip after the fabrication by TSMC. As you can see, this is the single coil and alignment mark and the respective ASIC. If we take a look at the detail of our circuit, we can see the capacitor, the LC tank, and level shifter and the output driver, as well as some electrical output. So this is the chip and the force contained interface zoomed in isotropic view. In our CMOS chip is 1.2 by 2 millimeter square, and our stainless steel sheet is 0.8 times 0.8 millimeter square, so it can be applied into the micro force sensor application field. And this is the device after the packaging. As you can see, the CMOS chip is fully encapsulated by the polymer, and the force contained interface is integrated by using the adhesion of the polymer. So let's move on to the measurements and discussions. So the measurements will be divided into electrical measurement and force response. Here we presented the LC tank frequency response by using the spectrum measurement. As you can see, our resonant peak of the LC tank is at 58 megahertz, which is a little bit different as compared with our simulation tools, and which may due to the variation of the CMOS electrical component. And we put a signal into the time domain, and we can see this kind of a periodic waveform signal output. So we demonstrate this kind of idea. But if you see further detail, you will see there has some lagging between the signal as compared with our simulation. So in the future, we may increase the current driving, or we can replace by using a digital counter to resolve that problem. And this is the force response of our testing setup. Device on the test is put on the triaxial stage, connected with the computer to control the position. And above is the loading probe connected with the force gauge to monitor the force applied on the sensor. And this is the device. We can connect it to the spectrum or oscilloscope to read the signal frequency output. So this is the measurement force response of our inductive tactile force sensor. And you can see the piecewise linearity is again appear due to the large deformation of the polymer, as we demonstrated in our previous study. And each of the loading range will have different sensitivity. And currently there is a 4-fold difference between the simulation and the measurement. And so in the future, we are going to categorize the different electrical property of our CMOS components to remodel into our simulation tool to compensate the error. So this is the summary I'm going to wrap up today. A simple approach to implement a solid-state micro-tactile force sensor is successfully demonstrated. In our design, the inductive sensing is chosen to realize the micro-tactile sensor to avoid using the suspended simple structures. The CMOS process platform is rendered to implement the microcoil and the circuit. The integration of the frequency counter and digital converter are demanded in the future to provide a better signal processing flexibility. So this is the acknowledgement. I want to thank the TSMC and TSRI for providing the CMOS platform. I also want to thank the Ministry of Science and Technology of Taiwan for providing the research funding, and also the IEEE Sensors Conference for providing me the opportunity to present my work here. So this is the end of my presentation. I want to thank for your attention. If you have any question, you can email my link down shown below, and I'm willing to answer your any question if I can. And I want to say thank you.